Hello everyone. Today we shall discuss third semester subject, that is discrete mathematical structure. In that we will begin with the chapter that is Introduction to Integers and Mathematical Induction. Now the first thing is, what is integer? As you all know that integer is a whole number, but it is not containing the fractional component. That means it may be positive number like 2, 4, 6, 7, 10, 50 and so on. Or it may be a negative number like -3, -4, -56, -100 including 0. These all numbers belong to the integer group. But whereas the number which is containing the fractional component like 5.6 minus 5.8, 3.3, 100.11. All these numbers do not belong to the integer group. So, what is integer? How to define an integer? Integer is a number which is not containing the fractional component. Next, now let us consider z. Z be a set of integers which is containing two distinct integers, say x and y. Here z is a set of integers and x and y are two distinct integers. Now which belong to the set z. Now the arithmetic operations on these two integers. Say for example, if it is addition, x plus y, subtraction, x minus y, multiplication, x into y, and the division, x divided by y. See, among these four, these three results belong to the set z, whereas x divided by does not belong to the set z. Why? Because this division is containing the fractional part. Now, let us consider an example. Let x equal to 2 and y equal to 3. Now perform all the arithmetic operations on these two. See, first one, addition. X plus y is equal to 2 plus 3, which is nothing but 5. And this 5 belongs to the set of integers. Next, x minus y, which is 2 minus 3, that is minus 1. Minus 1 also belongs to the set of integers. Next, x into y, which is 2 into 3, which is equal to 6, belong to the set of integers. Whereas x divided by y means 2 divided by 3, which is equal to 0.666. This do not belong to the set of integers. Why? Because this is containing the fractional component. So this is about a brief introduction of integers. Now let us start with mathematical induction. So what is this mathematical induction? See, let S of n be an open statement whereas k belongs to the set of integers which is nothing but a positive integer. In this case, the first condition, that is S of 1 is true. That means wherever there is n, you have to put 1. If that condition is satisfied, then you have to say that S of 1 is true. And the second one, S of k is true where k belongs to the set of integers. In that case, S of k plus 1 is also true. So, if these two conditions are satisfied, then we can say that the open statement S of n is satisfied, and whereas all the positive integers n which is greater than or equal to 1 is true for all the integers. So this is the basic definition of mathematical induction. Now, this mathematical induction, we have to carry out this based on two steps. The the first step is basic step. So in the basic step, wherever there is n in the given open statement, we have to put 1 wherever there is n. Then if we get LHS equal to RHS, then we can say that S of 1 is true. And the second step is induction step. So in this case, we have to put k wherever there is n. Later we have to put k plus 1 wherever there is k. In that case, if LHS is equal to RHS, then we can say that S of k plus 1 is true for all the integers n greater than or equal to 1. Now, let us start or let us solve the problems. Example, that is 1 plus 2 plus 3 plus 4 plus and so on up to plus n is equal to n into n plus 1 divided by 2. See, this is the given open statement. We have to prove that for all the integers n which is greater than or equal to 1 belong to the positive set of integers, that is z plus. So now, how to solve this? First step, that is basic step. In the basic step, let us consider the open statement, that is S of n equal to 1 plus 2 plus 3 plus 4 plus and so on plus n is equal to n into n plus 1 divided by 2. Now in this, let us take LHS. LHS is n. Now, S of 1 equal to what? Wherever there is n, we have to put 1. So, S of 1 is equal to 1. Hence, this is LHS. Now, consider RHS. RHS is n into n plus 1 divided by 2. Now, S of 1 equal to, wherever there is n, you just have to put 1. This becomes 1 into 1 plus 1 divided by 2. Now 1 into 1 plus 1, 2 divided by 2. 2 get cancelled and the answer is 1. You can see that LHS is also 1, RHS is also 1. Therefore, LHS is equal to RHS. Hence, the first condition, that is S of 1 is true for all the integers n greater than or equal to 1. So this is about the first step, that is basic step. Now let us do the second step. Now the second step is induction step. So, in the induction step, first you have to consider, you have to replace n by k. That is, we know what is S of n. This is S of n. Now, wherever there is n, we have to put k. Hence, it becomes S of k. Now, S of k is equal to 1 plus 2 plus 3 plus 4 plus and so on up to, this n is replaced by k is equal to, here also n is replaced by k. So this becomes k into k plus 1 divided by 2. Now, next is, so what is there in LHS in terms of k? There is only k. Now, you have to replace k by k plus 1. In that case, LHS becomes k plus 1. Now, you have to add this term on both sides. Now, the open statement becomes 1 plus 2 plus 3 plus 4 and so on up to plus. K is already there. You have to add k plus 1. So, k plus 1 is equal to this one, RHS. K into k plus 1 divided by 2 plus, you have to add this, k plus 1. Now, let us consider this k into k plus 1. If you take the LCM will be 2 and this becomes 2 into k plus 1. Now, I'll take this 1 by 2 outside. What is remaining now? K into k plus 1 plus 2 into k plus 1. Now, 1 by 2. Which is common between these two? K plus 1 is common. So, let's take k plus 1 outside. Now, the remaining is k and here it is 2. So, now, let me write this. I will write this k plus 2 as k plus 1 plus 1. Both are the same. So now, compare this with your initial equation. See, as we know that n is replaced by k plus 1. So you have to consider k plus 1 as n. Now compare these two. 1 by 2, n, there is k plus 1. Next, n plus 1, nothing but k plus 1 plus 1. So, this is how the second condition is also satisfied. That means S of k plus 1 is true for all the integers n greater than or equal to 1. Okay, so we can solve few more problems also. So now, let us solve one more problem, that is 1 square plus 2 square plus 3 square plus 4 square plus and so on plus n square is equal to n into n plus 1 into 2n plus 1 divided by 6. So what is this? This is an open statement given. We have to prove this. As usual, the first step, that is basic step. So in the basic step, let us take LHS. LHS is n square. Now what is S of 1? We have to put 1 wherever there is n. This becomes 1 square and 1 square is 1. Now RHS. So RHS is n into n plus 1 into 2n plus 1 divided by 6. Now you put 1 wherever there is n. So this becomes 1 into 1 plus 1 into 2 into 1 plus 1 divided by 6. Now what is this? 1 into 1 plus 1, 2. Next, 2 ones are 2 plus 1, that is 3 divided by 6. 2 3s are 6. Now this is 1. So if you observe this, LHS is equal to RHS. Hence, the basic condition is satisfied. Now, let us go for the second step. So now, the second step is induction step. So in the induction step, as we know that this n is replaced by k first. Then this becomes S of k is equal to 1 square, 2 square, 3 square, 4 square and so on up to plus n becomes k now. Therefore k square is equal to k into k plus 1 into 2k plus 1 divided by 6. So now, what is there in the LHS? That is k square. Now, replace k by k plus 1. Then this becomes k plus 1 whole square. Therefore, adding k plus 1 whole square on both sides. So now this becomes 1 square plus 2 square plus 3 square plus 4 square up to k square plus k plus 1 whole square is equal to k into k plus 1 into 2k plus 1 divided by 6 plus k plus 1 whole square. Now this will be, now which is common here? In both the cases, k plus 1 is common. Therefore, now if you take k plus 1 from both the sides, here what is remaining? K into 2k plus 1 divided by 6 plus, and here if you take only k plus 1, the remaining is k plus 1. Now, k plus 1. Let us take LCM. LCM will be 6. Now, k into 2k plus 1 plus, the 6 comes here, 6 into k plus 1. So now, this is, let us take 1 by 6 outside, k plus 1 divided by 6, and here if you cross multiply, you will be getting k into 2k square plus k into 1 k plus 6 into k, 6k plus 6 ones are 6. K plus 1 divided by 6. And now this is 2k square plus k plus 6k, that is 7k plus 6. Now k plus 1 divided by 6, and here we have to solve this equation. How to solve this equation? See, if you multiply, you must get 6 twos, that is 12. If you add, you must get 7. Which are those numbers? 4 and 3. Therefore, 2k square plus 4k plus 3k plus 6. Now, k plus 1 divided by 6, and here it is 6. If you take common in this, 2k will be common. 2k into, here left with k plus here 2 plus, here the common is 3. 3 into k plus 2. So, k plus 1 divided by 6, and here between these two the common is k plus 2, and here is 2k plus 3. Now see, k plus 1 divided by 6. Now I write this as k plus 2 can be written as k plus 1 plus 1. So both are written the same. K plus 1 plus 1 is nothing but k plus 2. Next, 2k plus 3 I write it as 2 into k plus 1 plus 1. See, if you multiply this, you will be getting this one only. We will verify that. See, 2 into k, 2k plus 2 into 1, 2 plus 1. So this is 2k plus 3. The same thing we are getting. Now, if you compare this last statement with the given open statement, we know that n is nothing but k plus 1. So if you just compare this, what you will be getting? N, that is k plus 1 into n plus 1, this one, k plus 1 plus 1 into whole divided by 6. So the second condition, that is induction step, is also satisfied. Therefore, S of k plus 1 is true for all the integers n greater than or equal to 1. So this is how the mathematical induction is done.